We've spent some time over the last week looking at objects with charges and what happens when objects do have charges. We spent some time yesterday looking at how those objects get their charges, how they become positively charged or negatively charged in order to attract something or repel something, and so on. We saw yesterday that there's two ways that we can charge objects. They were charging by conduction and charging by induction. Conduction and induction are different from each other in the sense that conduction always involves what? Conduction always involves what? Yep. The transfer of charge. It usually involves what? Right? Good. So it always involves a transfer of charge. It usually involves touching. Induction never involves a transfer of charge and never involves touching. Now, we break conduction into two subcategories. One's called charging by friction. That's simply rubbing two things together. Okay, you take a balloon in your hair, you rub it together. There's electrons transferred from either your balloon to the hair or the hair to the balloon. Okay, you take a piece of cotton and you rub it against a piece of glass. Well, the glass becomes charged. Okay, the cotton does too. So one loses electrons, one gains electrons. The law of conservation of charge still has to hold. If they started off as neutral and one of them becomes -5, then the other one must become +5 to keep a total charge of 0. Hey, by the way, the one that became -5, what happened to that? Did it gain electrons or lose electrons? Yep. Good. The one that became +5, what happened to it? It lost electrons, right? If you become negative, then you must have gained negatives. If you become positive, it's not because you gained positives, it's because you lost negatives. Charging by contact, which we sometimes just call conduction, involves physically bringing two objects close enough together to either touch or almost touch. Close enough where electrons can at least jump from one to the other. And that's the case. Charges want to balance out. They don't always balance. If the size of the object is different or the shape of the object is different, they may not balance, but the goal is to balance them out, and usually they do. All right, let's spend a little bit more time on the last one here, which is induction in the two categories within induction, temporary separation of charge and a permanent charge. Let's draw an object here that's neutral. It doesn't have to be a circle, by the way. Okay, it could be any shape. Okay, it could be a human shape, right? It doesn't matter what it is. Okay, it's neutrally charged. It's got an equal number of positives and negatives. Let's bring a positively charged object nearby it. What happens when the positive becomes nearby? Zach, what happens to the protons in that neutral object? No. No. What happens to the protons? Victoria, what happens to the protons? They're going to stay where they are because protons aren't going to move anywhere, right? They're in that nucleus. And what's going to happen to the electrons? Zach? Luca? Yeah, they're going to be moving towards the protons here. They're attracted to this side, right? Not all of them are attracted over there, okay? Because in the end, at some point, you get so many of them over there that the other guys just don't want to follow, right? Okay, but in the end, you get enough of them that you get this separation of charge with positive on this side, negative on this side. Hey, look at the side that's closest to the charging object. The negative and the positive, they're opposites, so they're going to attract, right? Charged objects attract neutral objects, always, because of a separation of charge. Hey, how would we make this permanent? Grounded, somebody said? In some parts of the world, they would call it earthing. Right? We call it grounding in North America. In some parts of the world, they call it earthing. Why do you think they call it earthing? Where would that term come from? Yeah. Yeah, you're attaching it to the earth, right? So this is our grounding wire right here. Now, it doesn't have to go down to the earth. It could go to some other object, and we'll show you that in just a second here. But generally, it's going to be attached by some kind of conductor to the earth. What's going to happen to the protons here now, Zach? Nothing. Protons always stay where they are. Okay. What's going to happen to the electrons here now? Well, these electrons still get pulled over to the right-hand side, but now you get this, all of a sudden you get this massive source of electrons down here in the earth. So the earth says, look, I got enough. You can have as many as you want. Electrons go up here, up through this grounding wire, go up into here, and make this whole thing negatively charged. How do we make it permanent? We're almost there. How do we make it permanent? Cut the wire. Take away the wire, cut the wire, remove the grounding wire in some way, and all of a sudden now it's permanent. Make sense? What would happen, quick little modification to this, what would happen if you just attached another object right here? It's touching. What's going to happen to that? Let's say it's neutral. This positively charged object is going to suck the electrons from the blue object to the right-hand side. It's also going to suck electrons from the red object as far over as it can. So now you've got a red object that is negatively charged, positively charged, and a blue object that is negatively charged, right? It's kind of like just a separation of charge here still, though, right? Because it's kind of like one object. But what happens if we separate them like this? Now you got a blue object that is negatively charged and a red object that is permanently positively charged, right? What have I just done? Is that not the same thing as what I did here a minute ago? Touching a grounding wire? Remember we said a few minutes ago, it doesn't physically have to be the Earth that grounds it. It can be some other big object that grounds it, as long as you have a good source and a good sink for electrons to go. Does that make sense? We'd still call that, by the way, that process would still be called what? Induction or conduction? I put another object nearby. I actually touched the other object. Electrons transferred from the red one to the blue one. Induction or conduction? We still call it induction. Why? Because the thing that's doing the charging, the thing that's causing the whole thing to happen, isn't touching and isn't transferring charge. Does that make sense? Even though there is a transfer taking place within the whole deal, it's kind of like conduction, kind of like induction. We call it induction because it always goes back to whatever is causing it, whatever is making this happen. In the end, guys, if you put a red neutral object and a blue neutral object beside each other and you touch them, and there wasn't this positively charged object over here, what would happen? Neutral, neutral, touch each other, nothing else around. What happens? Nothing. Neutral balances out with neutral to be neutral, right? So that's not our criterion for determining whether it's conduction or induction. This is the important thing. So that's what we use to determine whether it's conduction or induction. Does that make sense? All right. I want to show you a little device here. We've actually got one of these devices, although they tend not to work very well. It's called an electroscope. An electroscope is a device that's used to detect charge. Told you I wasn't really going to do anything new with you. I'm not, because this electroscope is based on principles that we've just learned. I just want to show you how sometimes those principles can be used to actually do something. Monday we'll show you some more examples. An electroscope doesn't tell us how much charge we have. An electroscope doesn't even tell us what type of charge we have, positive or negative. It just tells us whether we have charge or not. Here's two forms of an electroscope. First one is actually a photograph of an electroscope. Okay, it's kind of squarish. The second one is it's kind of a homemade electroscope in an Erlenmeyer flask here. The drawing of it. It's easier to see, so that's the one we'll use here. The electroscope consists of a metal ball up here, a conducting ball up here. Okay, it also consists of this conducting rod that goes down to these really, really thin leaves, thin foil leaves. These thin foil leaves can be made out of aluminum, they can be made out of gold, or made out of anything that's a good conductor, right? But when I say thin, they're thin. I don't mean like aluminum foil thin. Okay, I mean like, you guys ever seen gold foil like used for baking? You guys ever seen it? You know what I'm talking about? Like really, really, really incredibly thin. So much so that if you touch it, it kind of rips and touch it, it sticks to your finger, and it's so thin and so light. That's the kind of thing we'd be using. Not necessarily gold, but thin like that. Now, this electroscope has protons and electrons and neutrons scattered throughout it. Let's draw a few protons here. Proton in the ball up the top, proton in the rod, protons in each of the leaves. But there's also electrons scattered around as well, right? Which gives us more or less neutral everything. Make sense? What's going to happen to the leaves of this electroscope right now? They're going to hang straight down, right? There's no reason for them to do anything other than hang straight down because of gravity. But watch what happens when I bring a negatively charged object nearby. What's going to happen to the positives in here? What's going to happen to the protons in there, Zach? Good, nothing. Protons stay where they are, right? What's going to happen to the electrons? Justin, what's going to happen to the electrons in here? Nothing's going to transfer, unless these guys are really, really close, and let's assume they're not close enough to jump over. Derek, what's going to happen to the electrons in the electroscope? Good. They're going to be pushed down. So this guy, they're going to get pushed down to here and here. Look at the leaves now. The leaves were neutral. Now they got more negatives than positives, right? If both of these leaves are negative, they're not going to hang straight down anymore. What's going to happen to them? They're going to repel each other, so they push apart. Does that make sense? We've just detected charge. It doesn't tell us that we had negative. It doesn't tell us how much charge we have, but it tells us we got charge, because these leaves don't spread apart. These leaves stay straight down in the absence of charge. Hey, quick little question here before I switch this diagram around a little bit. What if I ground it? What if I ground it? What's going to happen, Bryce? Nope. How come you think they go back to the original? Because it'd be negatives going in, like from the ground? No, just the opposite, in fact. These negatives want to be pushed down into the leaves, right? Unless it's grounded. And then these negatives want to be pushed down into the ground. The grass is always greener on the other side of the fence, right? These electrons want to go to these leaves, but hey, wait, look, we just opened up a whole new world, literally, the Earth. So what happens? The electrons say, I'm not going to go down there. I'm going to go down into the Earth, right? Hey, quick little question before you leave here, guys. I won't redraw it, but what if I had brought a positive object nearby? Forget about the grounding here as well. What would happen to the electrons in that case? They would have got sucked up to the ball, right? Leaving the ball negative and the leaves positive. What would happen to the leaves? They would repel again. So again, it detects charge, but the leaves are going to do the same thing whether you got positive charge or negative charge, right? Doesn't tell us what kind we have. Make sense? All right, have a good weekend, everyone.